Okay, so uh, start then. So, hi everyone. Welcome to the EPMA's webinar on 100 years development of hard materials. The German inventor Karl Schroeter filed a patent titled Sintered Hard Metal Alloy and Production at the German Patents Office in Berlin on March 30th, 1923. This was the beginning of a new era of hard metals or cemented carbides. Hard metals today form the backbone of tool manufacturing industry with diverse applications used in mining, construction, cutting, and structural applications, promoting many fields of production technology. This webinar is a roundtable meeting of the experts from hard materials world who had many years of experience and observations on the evolvement of this amazing industry. EPMA's Hard Material Group EuroHM is bringing them together in this online event to share their knowledge and memories that will be a big benefit for engineers, scientists, and other related parties working in this field. All our speakers have been quite active at EPMA in the past with different roles, and our moderators of today are actually the co-chairs of UPMA sectoral group of hard materials, that is EuroHM. Now I want to introduce you one by one our speakers. The first one is Colette Alibert. Colette graduated from Grenoble Institut National Polytechnique in 1964 and received her PhD in material science in 1971. She worked as CNRS scientist in LTPCM. This is the Laboratory of Thermodynamics and Physical Chemistry up to 2005, where she was strongly involved in powder metallurgy. Presently, she is working voluntarily in APIT as an honorary president, which is the Association for the Heritage and History of Industry in Dauphiné in France. Our next speaker is Hank van den Berg. Hank is a former director of innovation and R&D at Kennametal, and he retired in 2016. Hank received his diploma in physics from Aachen University in 1975 and achieved his PhD in theoretical metallurgy at the same school. And then he worked mainly on coating technologies at Vidya as manager and director until 1980, until he retired. Hank is the inventor or co-inventor to various inventions in the field of hard materials and coatings for tools with more than 25 patents. Uh, our third and last speaker is Bjorn Urenius. Bjorn received his Master of Science degree in 1966 and a PhD in 1971 at the Royal Institute of Technology in Stockholm. He started his career as manager of R&D at Avesta Works AB in 1975. Then he has been the R&D manager of Sandvik Coromant in 1981. He is elected as member of the Royal Swedish Academy of Engineering Sciences in 1994, and he has been the vice president of R&D at Sandvik Hard Materials and the president of CERMEP in France at the same year. He's been awarded several medals in 1976 to 2001 from the Metal Society UK and EPMA. So now I would like to introduce you both our moderators as well. So I would like to start with Susan Norgren. Susan is the global expert group of Sandvik, and she's also adjunct professor at the Division of Production of Materials Engineering at Lund University in Sweden. She had her MS and PhD degrees at KTH Royal Institute of Technology in Sweden, where she did her habilitation in 2007. She has been adjunct professor in trilogy at Uppsala University for 10 years. She's been taking several roles in Sandvik Coromant and Sandvik Mining since 2000, and currently she's the chair of mining and material divisions at the Swedish Royal Academy of Engineering Sciences, and as I said, she is co-chairing also, the EPMI, the Institute of Powder Metallurgy of EPMA. The last moderator person I would like to introduce is Brian Robach. Brian studied metallurgy at the University of Manchester Institute of Science and Technology from 1964 to 1967. Brian joined NPL, the National Physics Lab in UK in 1970 to work in the deformation and fracture group of materials division on a new joint venture with the research group of the British Hard Metal Association led to Wimet Coventry, which is known as Sandvik Hard Materials now. With more than 50 years of experience in hard material tooling technology, Brian provides international authority in relevant meteorological science. As of today, he is an MPL Emeritus Senior Fellow, and he also provides a science mentoring role, particularly in the materials group, contributing to the project and strategy meteorology initiatives. So thank you for joining. It is very long introduction because our speakers have been really strong experts in their fields. So there are actually many more other things that I couldn't put here. I just summarized what they have been doing for in the past for hard materials. So now I would like to give the floor to Brian, but before that, I would like to make a short announcement. In case you want to ask a question, and please do not hesitate to do that, you can either raise your hand by clicking on the hand button on the top of your screen, or you can put your question in the chat where I will read it orally to our related speaker. So now I would like to give the floor to our moderators, to Brian first. So Brian, the floor is yours. You can please unmute your camera and unmute your microphone and turn on your camera, and so you can go on. Thank you.
Well, welcome everybody. What a unusual meeting this is going to be. Something I'm really looking forward to, having worked in the area for more than 50 years, which is a rather a long time. But then again, it's only half the time from when we started with hard metals. So it makes you think about all the things that might have happened in the 50 years leading up to my start in the area. And I think that gives me the point to introduce Henk's presentation, where I'm hoping to learn a lot of things. Okay, Henk, it's down to you.
Hello, Ken, could you bring the presentation on the screen?
Yes, one moment, please.
Thanks. Yes, here we are. Well, let me start. Thanks to the EPMA for the invitation that I could give after my retirement. Again, a little historical talk about 100 years of hard metal. It all started, next slide, please, Ken. It all started, what Ken mentioned, with the Carl Schroeter patent on March the 30th, 1923, which was a common work in the Osram institutes in Berlin. Also, Mr. Scalpi was involved. That name will come back a couple of times. And after using this material in drawing die for making filaments, it seems that Osram was no more interested to do more research on applications. So Krupp acquired by the end of 1925 this patent and started the manufacturing in 1926. You see a first structure of the Widia N, tungsten carbide 6% cobalt grade, which is still today one of the most used compositions. And in the next slide, please, Ken. Krupp was very good in marketing. Alfred Krupp already had a huge marketing department starting in the 1850s. And Krupp decided the baby should have a very good name. And they had a discussion in December 15th, 1925. You see it on this envelope. from Mr. Drotz and Mr. Preusing from the patent department. Widia was a suggestion, B-carbide. Cardia was a suggestion, cardi or wocar. But finally they choose the word Widia, and this stands for we diamant, as hard as diamond, and is still registered till today worldwide and protected as a trademark name. And from that, the success started. Next slide, please. It started all in the basement of the Krupp laboratories, not far away from the production site, which we will see later on. And it is very interesting that at the same time, the company Walter, Mr. Walter, started the production. But looking to the files in the historical archives of Krupp, he had to make an agreement. And it's very funny to see that Walter has then, for years in their catalogs, to have a special page at the end that their products are made out of hard metal blanks from Widia. Some witnesses in 1951, when they celebrated the 25 years, it was quite nice to read that it was really hard for them in the first months. When they start production, they had explosions because of the hydrogen what they used. But it was mainly Mr. Dr. Bruno Strauss, who is the inventor also of the Nirosta, the corrosion-resistant steel, who keep pushing and pushing this material, and finally they could make 1,067 kilogram hard metal, as we can read in the files, in the first years. And after that, next slide, please, followed, of course, the introduction to show it to the world, and it was really a sensation at the Leipzig Fair in 1927, when they showed machining of cast iron with tool life, which was really incredible for those days, the change from HSS steels to this new sensational material. Next slide, please. It was very early then decided that a brochure was made in the beginning, and this is the brochure from 1930, so only 4 years later, in 6 languages, written and worldwide distributed already. And it was very important what they saw, that from the start of the introduction, the training, how to use cemented carbides is the key factor in machining. Even now today, the application of cemented carbide on in the machining, on the tools that are, of course, nowadays quite complicated, is the key point in training the people that are at the machine. And that was a success in Germany, especially in Europe at those days. And when you read the booklet where Dr. Ammann is visiting the United States in the years 1935, 1936, to see how and why the carbide is not having there a breakthrough, it was this kind of not trained people that very, very often the cemented carbide tools used in the US were just breaking because of the application was done in a wrong way. The next slide, please, shows the really sensational tool life improvements, as you can see here, by factors that were unbelievable. It can be compared, these huge graphs, what you see with the enlargement of the productivity of the tool life is only repeated years later on. We will come back to that when the coatings were introduced. Next slide, please. Again, here you see the very, very broad application guides, what they gave directly after introducing a new product, a new material. Here the slide X8, a new grade. And very important, every time in these brochures was the application with pictures, with a layout, how to use it, how to approach the part you want to machine, and even how a machine has to be constructed regarding stability and the clamping of the parts. The next slide, please. This is quite interesting when we talk about pricing, because it's really a very good business. Although in the machining today only 4% of the costs are the cutting tool, but the pricing, the usage was from the beginning very, very important. And it's really amazing that in the mid-30s, it was $45 per pound, because it was sold per weight in those days. And in the United States, as you can see, it was in the 1920 around $50 per pound, sold by General Electric under the name Carboloy. Between the 30s and the 36, it was $450 per pound. It was amazing what Herbert Ammann saw in those days. And after that, it came back to about $100 per pound. So it was really more expensive in the United States in those days, what they stated, than gold. But also here you can see again that these pricing, which were done in those days by Krupp and the company Zepp in Düsseldorf, were worldwide done per kilogram, per kilogram. The next slide, please. This is the picture of the plant in 1934. It was taken from the first handbook of hard metals given in those days, published, and in that factory, really the usage and the tonnage was dramatically increased in those days, because the production of hard metal was really now under control, and a lot of licenses were given to other companies. And in those early days, it was really worldwide the breakthrough. Of course, after the World War II, the production was stopped for 1 to 2 years, but very soon there was allowed again from the British Council in those days in North Rhine-Westphalia that Widia could restart, but they have to write down, and that is a very interesting booklet, the so-called 1-point hard metal Bible, where Mr. Scaupi have to tell everything, how to make hard metal, all the grades, all the machines, all the equipments are written down. And after that, of course, the German hard metal industry, but the worldwide hard metal industry was growing very fast. And today in Germany, just some names. You have Walter Company owned by Sandvik. You have Göring, Element 6, Horn, Conrad Friedrich, Saar Hard Metal, Tigra, Tribo, the former East German hard metal production site, Durit, Carbidur, Betec, Mapal. So you have really a huge number of hard metal producers in Germany who make partially also their own powder, but on the other hand also buying blanks and make out of these tools. Some breakthroughs in the next slide, please. During the next developments were the clamped, the mechanically held inserts in the mid of the 50s, very broad, introduced in those days by Sandvik. But it was already first Sterling in 1930 who had the Mechani gripped and some tool holders by Widia to the left side down out of the handbook of Karl Becker from 1935, which is a very broad booklet about hard metals and about application of hard metals. And finally, throwaway tips were introduced in the 50s, as I said. But Widia pushed very hard that they said, well, we do not throw away our inserts, and the name was changed in indexable inserts. The next slide, please, was a breakthrough that came in the 1960s, mid-60s. The first announcements were made in Werkstatt and Betrieb by Professor Rüdiger. However, this was a heat treatment of cemented carbides where a top layer was produced by sintering, which was then called a coating. But the first coatings really were made in 1969 on the market, a simple titanium carbide coating, followed by a titanium carbide tin coating to the right side. And the next slide, please. The very broad introduction then by aluminum oxide coatings was a breakthrough also to go to much higher cutting speeds, very broadly introduced in those days by Sandvik, by a titanium carbide aluminum oxide coating, followed by multi-layer coatings, and nowadays, next slide please, the approach to make really a good performing cutting tool, because we don't sell a coating, we don't sell a hard metal combination, we sell a cutting tool, a cutting edge, in round tools or in inserts or in wear parts, name it. It's the substrate, very important. It's the cutting edge, it's the coating, it's the chip breaker geometry, the design, how to lead the chip out of the workpiece to machine. Later on, in the beginning of the 2000s, 2001, the stress was introduced in CVD. It was known by PVD that you have compressive stress, and we had also always tensile stress in coatings, and we found out how to change that by blasting processes, by post-coat treatments. And very important came up, especially pushed by company Sandvik, was I call it the texture management of the aluminum oxide layers, which gives again very good improvements in machining performance. But these components, as you can say, these 5 components are very important to make a very good cutting tool. When we talk to some outlook, the next slide please, in the future, we will have change. It's ongoing already in aerospace and automotive. We go to electro cars, which will have, of course, an impact in the number of machining components. The introduction of 3D printing and the change in machining will be followed of that. We will have more finishing to finish the 3D parts. We have to use more recycling because the resources availability are limited for sustainability. There will be a strong focus ongoing already on increasing productivity, optimal application. There will be optimizations in ceramics, hard metals, the geometry, coatings, texture of coatings, stresses of coatings. So there is a lot of work to do. Improve production technologies like the powder processing, pressing, extrusion, sintering, coating, and of course 3D printing. We have to go faster to market. And of course, very important today, you can read it in every newspaper, in every market, but also in our industry, is the development of better networking to support talent development needed not only in research and development, but also skilled co-workers in production. You really need skilled co-workers in production to do the sintering and to do the pressing, etc. Next slide, please. An outlook is that our community is very creative and dynamic. As a retired guy, I still follow some of the developments, and it's really very nice to see what is happening and ongoing. The industry are giving our community the challenge, of course, to improve their productivity by new materials, new machine tools, concepts, automatization, cost per parts program. So the pressure from the industry to us will be there, and we should never forget that the industry is paying our salaries. And working closely with our customers is very essential to understand the needs. So the researchers should not sit in an ivory tower, but they should really know what is outside needed, as the hard metal community has done in the last 97 years. And I think by doing our homework, the success story of our cemented carbide will continue. And the last slide from my short overview is that the number of tools are really great at the moment. We always have the target for the ideal cutting tool materials. There are a long way to go there, but seeing now the high temperatures alloy, high entropy alloys using and other technologies will really further improve the performance and to give a better productivity to our customers. So it's really great, and I will really see that the cemented carbides are now 100 years part of this family, and they will have a very bright future. Thanks for your attention.
Okay, thank you, Henk. That was a tour de force, really, of what happened from the start, right from the start. Just to remind everybody, what we're going to do is just go through those first four speakers, just to set the scene. So Henk was the starter, and the second one is going to be Bjorn Uranius. So Bjorn, are you ready to go? Yes, we can see you, Bjorn, but not hear you.
You hear me now?
Yes.
Oh, it's okay. Hello.
Okay, Bjorn. So I hope we're going to hear a lot about what happened in Scandinavia.
Yeah, yeah, okay. So can I have maybe the first slide? The very first one is up here. This is the cover, yeah. Why I'm here is because of the Swedish Ironmasters Association, Järnkontoret, as we say in Sweden. They started 5 years back in time to do a review of the development of powder metallurgy in Sweden, and that does not only cover hard materials but also iron powders and steel business. But a part of this book, which was released in February this year, is the hard material. Is about 100 pages in this heavy book about cemented carbide, as we call it in the book. I must say that I am honored by you, EPMA, and also by the Swedish group to be a member of this, because I'm since 20 years retired from the business. So my knowledge is outdated maybe to some extent. But anyhow, I was asked to collect a group of scientists and production people who could write about the Swedish history of cemented carbides. And we were all together 17 people who have been contributing to this chapter in the book. Can I have the next slide? Yeah, and you have already mentioned, Henk, about Sandvik and so on, but Sandvik was not very near to be the first in Sweden. After the Schröter patent in 1923, there were also a lot of efforts to sell cemented carbide in Sweden by Vidya and so on. And there was a small company, Arbit in Arboga. They had some German links. A owner or the capital was partly financed by Germany. They started to make fused carbide, but later on they went on and made their own cemented carbide. And they had the first Swedish patent offered in 1929. And they launched this Sintram as a brand name in 1931. But they focused a strong competition both from Vidya and also from Fagersta, who were interested in switching partly from the steel business to making cemented carbides. And then in 1932, they launched the brand name Seco, and finally Grönvall and Gottlieb Larsson was the owner. They found that the competition was too strong and they had not the resources to go on. So their business was sold off to Seco. Next slide, please. At the same time as in Germany, the Swedish bulb manufacturers were facing a strong competition in Sweden by Osram, and the cooperative business in Sweden, they saw that the prices were too high for people in general to afford buying these bulbs. So they started to build an own factory, and they started that in the harbor of Stockholm in 1930. And here is a picture of the factory in 1940. It was a huge thing. And the cooperative society, they decided that the chair or the manager of this factory was Heinrich Schlott, who had a background from Osram in Germany. And he started up this business and made it very, very successful. The first thing was naturally to produce tungsten filaments then for the bulbs, but also wire drawing dies out of cemented carbide. But he was not keen on investing in other areas for the use of cemented carbide, so he contacted other companies. May I have the next slide? And today, we have two major companies in Sweden producing cemented carbides. One is Sandvik, mentioned earlier, and one is Epiroc, formed from Atlas Copco or Atlas Diesel. Here we see on the left a rock drilling machine. It was a very successful invention by Atlas Copco at that time. It was a one machine, one-man machine, where you have a pusher leg and a pneumatic hammer. And this together with the rock drilling bits of cemented carbide, mainly at that time produced by Sandvik, were well known not only in Sweden but also over the world as the Swedish method for producing rock drilling equipment. I could say that in 1947, Sandvik and Atlas Copco started a joint venture. Next slide, please. And they focused then on the rock drilling business. And the rock drilling was successful not only because of the machines, but also on the bits you can see here on the picture. This cooperation lasted for more than 40 years and ceased in 1987, where Atlas Copco wanted to have their own cemented carbide production, and Sandvik then looked for another supplier of machines, and they formed a cooperation with Finnish Tamrock. But another important area, as mentioned earlier, is also metal cutting. Metal cutting tools was not considered very important in the Sandvik group from the beginning, but due to strong person Wilhelm Haglund as a head of a part of this business in Sandvik, he convinced the board to go on also in the metal cutting area. Next slide, please. So how come that small Sweden could be a major player in this area? Estimates made by the salespeople at Sandvik and Epiroc. Epiroc was later formed by Atlas Copco and Secoroc, which Atlas Copco acquired later. And just a couple of years ago, the rock drilling bits business of Atlas Copco formed a separate company named Epiroc. So these two companies together have in 2019 about 45 billion Swedish crowns yearly sales related just to the cemented carbide pieces. And estimates were that about these companies, mainly in rock drilling, have about 50% of the world market, and then a little less than in metal cutting. Next slide. So here is the inauguration of the cooperation, where Wilhelm Haglund to the left from Sandvik Coromant shake hands with Kurt Belfrags, was the managing director of Atlas Copco. Next slide. Another part of the business is wear parts. It's a very minor part in the group, but due to some acquisitions, both from a company in Örebro, Svenska Dragskivor, which were mainly for drawing dies for rods and wires, but also later on Sandvik made rolls for rolling steel, and also tire studs and many other wear parts. But one major thing are these roller cutters, rotary cutters you can see, which were invented in France, in Grenoble, by the Sandvik Hard Materials part of the business there. And there were two inventors there, Gerard Romagnolo and Daniel Tartares, who were very successful in launching rotary cutters there for cutting sanitary napkins and many other things. And they were so successful that they were awarded the Wilhelm Haglund Prize for the best product of the year. Next slide, please. So how has this developed? Yes, to the left, you can see a picture from Epiroc, how mainly the machines have increased the rock drilling speed here from a few 100 meters per hour until more than 300 meters, mainly due to machines, but also due to the development of the cemented carbide bits and the structure of the cemented carbide. To the left, you can see, as Henk already mentioned, there is a tremendous development in the metal cutting area. You can see how indexable inserts introduced, and then the coatings in 1969, mainly titanium carbide, but later also aluminum oxide. but also important thing is you can see to the upper right there, insert with a very strange ship breaking facility introduced by Walter, which was later a part of the Sandvik group, which made an enormous impact on the machining performance. Next slide, please. So Sandvik then decided that the factory in Luma, they were not sufficient to cope with this demand. So they started to build a new factory in Västberga, south of Stockholm, which is to the left here. It was inaugurated in 1955, I think. And when I first had a short employment there in 1973, I think we were more than 800 people working there and about 100 researchers. And through the whole history of the Sandvik development is that a philosophy formulated in 1860s by Anders Henrik Göransson, the son of the former of the Sandvik group. He formulated that we should focus on niche products, we should market through own channels, we should work closely with the customers, and we should develop the products in cooperation with the customers. And that has been successful and is so in the future, I guess. And to the right, Seko Fagersta, which had a down period in the 50s, and they realized they had to focus on cemented carbides too, and they built this factory here in Fagersta, which is a huge part of the group as well. Then comes to the history. Sandvik acquired a part of Seko in 1973, and the history behind is that Seko had severe, or Fagersta had severe economic problems, and the shareholders asked them, you have to sell off your cemented carbide business. And then General Electric, through Carbolloy, they offered to buy Seko. But the Swedish government didn't like that idea because they were in fear that the factories would be closed and transferred to United States. So they asked Sandvik, can't you come in and make an offer you too? And in 2 weeks' time, a settlement was agreed that Sandvik took over 2/3 of the shares of Seko and the rest remaining third by Seko. So that has been a close ownership, but still a very strong competition between these two, Coromant and Seko. Next slide, please. And I would say that two strong persons are behind. And then one is Carl Bontron at Fagersta, who realized that we have to focus on cemented carbide, and he got Seko running very well, and in particular in the milling area. And Wilhelm Haglund, he was successful in convincing the board of Sandvik go on with the cemented carbide, and he was so successful that he later on became the chairman of the whole group. I think this is the Swedish history of it. That might be my last slide, isn't that true? What is the next slide? Do I have a next slide? No.
Thank you very much, Björn. So interesting to hear.
This is the very, very special Swedish part of the history. There was many links in the beginning to Germany, but also to UK, where in particular wear parts came in due to the focus on very fine grades made in Coventry. So PCB drills was one project for a while. Now I don't know the situation exactly because it's 20 years since I left the business. Okay, thank you.
Thank you very much, Björn. And
Thank you,
Coventry is
Björn.
today a Corman facility. I was also intrigued, and it was very interesting to hear that Sandvik regarded the metal cutting business as a minor business and maybe didn't
That was a hard fight. William Haglund, he went up to the board for a meeting and had one of his co-workers with him, and they put down how little money Sandvik offered for metal cutting and said, how can we succeed with that minor support from you? And then he got 1 or 2 years with new money and show what you can do. And then he succeeded, really. So that is him we have to thank.
Thank you very much. So interesting. With this, I would like to hand over to Colette. Please, Colette, can you tell us a little bit from France?
And I want me to close my camera for a while. Oh, okay.
Is it okay?
Yes, it's okay. We can hear you. And now you're muted. So let's see. Can someone unmute Colette? Can you hear me, Colette? Colette, you're muted.
Is it okay like that?
Yeah, now we
Yes,
can
now
hear
it's okay.
you. Please start from the beginning again.
Okay.
Yeah.
As I said, I was a scientist, and so my comments will be more on the research development purpose, not really on the application. But anyway, there was a very strong collaboration with Sweden, and Björn gave already interesting results for the production point. Concerning the contribution of France in the hard materials, I would like to remind that to prepare hard materials, it was necessary to have tungsten and also tungsten carbide. For tungsten, Sweden has been the first finder of the oxide, and the metal was extracted by a Spanish student. I think it's good to remind the name of Fausto del Elua, in the 17th century. And the French contribution is due to Henri Moisson. He was a druggist. He became chemist after. And in fact, he prepared very high melting compounds, carbides, and tungsten carbide especially. And also he invented the arc furnace that was able to produce the high temperature to make these carbides. He got the Nobel Prize in 1906 for that. And this contribution was really important to introduce the hard materials after. Then it's also important to remind the introduction of powder metallurgy by a small industrial, Johannes Bocuse, the same that the famous cooker, but not the same script. He was in Lyon, and he was a wild drawer of gold and silver, but as at the beginning of the 20th century, silk industry was really weak, decreasing. He was interested in electric and electronic development, and he contribute to the to make possible the why for lamp TM, that is to say the bulb for military transmission, that was the ancestor of radar. And in 1990, he was, well, maybe not courageous, but maybe it was really their personage. He went directly from the gold wire to tungsten wire. And he prepared in the small firm of in Lyon by powder metallurgy, so reducing tungsten oxide, preparing tungsten powder, sintering and draw wire directly in this small Bocuse firm, and this for a long time. But for the hard materials, in fact, the beginning was made only under licenses bought to Carboloy mainly, or as subsidiary of group by Carbon Lorraine and several small firms that were about everywhere in France. For example, Sika Metal, Safety, that maybe still exists, Sofa Metal, but the most important was Carbon Lorraine, that was already expert in the process of powder and sintering fabrication, because he produced graphite pieces and many other carbon-based pieces. So, in fact, the beginning was about from 1930 to the first to the Second War. And in 1938, Carbon Lorraine had to pass the line that was occupied in France, and he found a good place really in the Green Country at Épinouse here. It is at the border of two departments around the Rhône River. and it was a good place to put some equipment and to prepare not only carbon pieces but also some carbides. So this is the place here, and the development took place just after the war. Here you see on this map, in fact, the land around Lyon and Grenoble was concentrated the main firms that develop powder metallurgy, and the other places who were concentrated, the firms were around Paris. From that time was created Usine Carbone in Grenoble. Maybe I can have the second slide, Kenan? No, maybe not. Well, this is the place where this is the usine des eaux claires, so who opened at the beginning in 49, and you see the entrance at that moment, and I show that because today the direction of the plant try to keep the style that is typical of the industrial architecture of the 20th century, and try to keep the style at least at the entrance, but also for the other building. And as we are here, may I have the next slide too, please? This is the site of Épinouse, as it was in the 40s, and the site now. It was constructed with an architecture that is very logical, close to a station, railway station. At that time it was important, and it was in fact constructed to receive the materials at one part of this line of buildings. All the operation took place here, control, analysis, and here you have the good pieces that can get out and be sent by road or railway, so that the plant is always used now, completely fitted at the inside, but always with the same type of architecture. Thank you. So to come back to the history, Usine Carbone, may I have again the first, please? Yes, so Usine Carbone began in the 50s, and the other firms that were created, in fact, also had a small department of hard materials. But quite rapidly, it was clear that mainly Carbone Lorraine at Épinouse and Usine at Grenoble were the main producer. They joined together. They formed the joint venture Usine Carbone, and they continue together for several years. In fact, in the 70s, the economic situation and the geopolitics problem induced a lot of troubles, and there were a lot of cuts, a big shrinkage of the production, and finally the hard materials part was sold to Sandvik in the 80s, in the 1980s years. And from this moment, there was a strong collaboration between scientists and research development in the plants. And I think that our contribution to the good knowledge of phase equilibria, for example, were very useful to define the best composition of the materials for depending on the use, and also to define the process of sintering. But what has been important also, I know that it seems to be far from the application, but however, I think it has been very important, was the contribution to the control of the microstructure by the fine analysis of images and of the interface. And all the works that were done, in fact, showed, but it was difficult to analyze the strong relation between the powder production process and the hard material constitution and microstructure, and the strong contribution of the interfaces. We are a little bit far from all the results that were applied to increase the control of the microstructure, but we know that it has been useful mainly when you try to keep fine grains to prevent the abnormal grain growth and any kind of defects in the microstructure that in fact rule the best properties of the materials. So this type of collaboration continued, and the production in France is mainly now under the umbrella of Hyperion for the hard materials. But at the end of the 20th century, the powder production was related to the hard material production in Grenoble. They had been separated at that moment. The powder production is under the umbrella of Umicore now, but it is clear that the relation has been very useful in the past, and I think that it is still useful now. Okay, so for the disruptive facts, I don't really know what I can say about the products that were very important. Bjorn Uranus spoke about the pieces to cut very rapidly the pharmaceutic, the health protection. There was also something that is quite maybe a side product, but important, the pins for the pneumatics to drive on ice that are always produced in a separate film. But there were also improvement in Grenoble with coatings and with the compatibility between coatings and substrates. But I am afraid that I cannot say more about the very important application from that. Oh yes, I would like to mention a very early process of recovery of the hard materials, of the metals in the hard materials using the zinc process. That is to say, dissolution in zinc and then boiling of the zinc vapor and recovery of the metal. But sadly, this invention was not protected. And I know that it diffuses quite rapidly in the competitive in the other firms. But nowadays works on the recovery of materials is also very important, but it is mainly the part of the powder production with Umicore. So I think that I will finish with this part. So, Brian.
Thank you very much, Colette. Really, really nice to hear. Interesting. And I have a little bit problem with the sound, I think, but from a personal point of view, of course, I have read your articles on interfaces many, many times. And I also, and likewise, as you mentioned, it's also important to remember the equipment that was needed and also the knowledge about the sintering, for instance. So thank you very much for that. I would say that. And then I also take the opportunity that I would like also to thank both you and the other grand lady who is not with us today, and that is Silvana Luix, because you were really the two front figures that you were also being women in this male-dominated business. So thank you for that. With this, I would like just to turn the word over to Brian. You are a moderator, but you are also very knowledgeable in the hard metals development within the UK. So please, Brian.
Okay, thank you, Suzanne. Yes, I don't have any slides, so you're just going to have to listen to what I say carefully. But really, I'd like to tell you the story of how the National Physical Laboratory got involved with the hard metal industry. And as everyone knows, after the Second World War, the hard metal group in the UK was instrumental in traveling to Germany and collecting all the information about the manufacture of these materials and then distributing it mainly to the rest of Europe and the USA, but it was available quite well. And that brings me to the point at which I got involved, which was around about 1970. And in the late 1960s, the British Hard Metal Association approached the Department of Trade and Industry and to try and get some scientific support for the industry and its manufacture of these materials. And after several meetings, it was decided to ask both the National Physical Laboratory and something called the National Engineering Laboratory, which is based in Glasgow, to independently prepare a report about what they might do with a project to support the industry. So it was a competition. And cut a long story short, by the end of 1969, MPL won that composition, and the members of the British Hard Metal Research Association and thought that the objectives were far better than the proposal put forward by the National Engineering Laboratory. So after some further meetings, the government agreed to do a project where it was 50% funded by the government and 50% funded by the industry. And at that time, that was about £20,000 in 1970s money, which covered about 3 people. So it funded, there were more than 3 people involved, but it funded about the equivalent of 3 people. And just to give you a feel for what that is, with inflation, that is now around about £450,000, which is quite a thought, really, to think about. So that got the project underway. But MPL were very tight on the number of people that, or the skills of the people that they had available. And it just so happened that I'd sent a letter asking if I could be interviewed for a job, just out of the blue. And I got an interview, and I got through it, and I ended up in a group which was led by a scientist called Eric Armand, who you may know from some of the old papers on hard materials. And it was Eric that had written the report that had won the competition with the National Engineering Laboratory. So 50% of my time, right from the start, was involved with helping the British Hard Metal Association. And it was quite formal. We had 4 meetings a year, every quarter, at which we had to report at least something of interest to the industry, which was quite a challenge in those days. And you can imagine now, having 4 meetings a year is quite a lot. Just to give you a feel for the types of people types of companies that were involved, I've got a list here of a few, and I won't give you the name. Well, maybe I'll give you some of the names, but Carbaloy was one, which was the American company. Day-Night Hard Metals, which were based in Doncaster. Firth Brown Tools were based in Sheffield. Wimmet Limited, which eventually got taken over by Sandvik. Sojimin, which was a raw material company based in France. Boat UK, which was part of the South African organization, which is part of the diamond manufacturer organization now. A few small companies, Edgar Allen Tools, Dimetalloys, Anderson Strathclyde, Syntride. Then there was a big raw material company, London and Scandinavian Metallurgical Company, which you may have heard of. And finally, Kutanit Limited, which was part of the Planze organization. So you can see with all those foreign contacts, it was quite a thing to go to these quarterly meetings where we would have a room full of 20 or more people every quarter. And essentially, the first topic that really grabbed their interest was electron microscopy. And this was because they were making the materials, and for the large part, there was an interest in the finer grain materials. And using optical microscopy, it was a real challenge to actually see what the materials had been made. So my first task was to use something called ion beam technology to prepare thin foils of the material and to examine those in what was called a million volt electron microscope. It turned out later that we didn't really need a million volts. It was okay to use about 200 volts. 100 volt was the typical electron microscope. So we were able to do a lot of work looking at defects in the structure and the size of the material. And following that, electron beam technology came along as well, so that we could do polish samples and look at the orientation of the grains. So that was really important, and we managed to publish a fair amount of work on that subject. And it also led to me being able to travel. And I can remember one of the first outings I made was to Sandvik in Stockholm, followed by Vidya, and then to Planze, just to go and talk to the various scientists there. And that was a real eye-opener for me, because everybody was very open and enthusiastic, keen to see that the UK was getting involved in this technology. So it worked both ways. I learned a lot, and I hope over the years since then we've contributed something to this community. But to give you a sort of an idea of what the topics we looked at over the first 20 years or so, that was from about, well, maybe a little bit more than that, maybe 1970 to 1990s, was to look at mechanical testing, first of all different aspects of that. Then to look at binder phase composition. So that's the carbon content and its effect. And tantalum carbide and titanium carbide additions. And then we followed that up with a project on substitute binder phases. So that's actually making materials that might have properties that would be useful in binder phase materials that might have properties, and then making the hard materials. And we did it in a slightly different way, which is you might find of interest, in that we infiltrated materials that had already been made. So we took a hard metal that was, say, probably 10%, 8% binder phase. And then what we did is we had a little groove on the top of the sample, and we manufactured alloys and placed small amounts on that groove, took it back up to the sintering temperature, and then the material just infiltrated into the hard metal. and we were able to make new materials. And this is something I think could be worthwhile revisiting as a means of trying to study new compositions rather than making it from scratch. Try and use the infiltration method, and that took us to probably the late 1980s. All of this material, by the way, the reports that we wrote are all available. They're not. You would have to come to MPL to ask for copies, and they're extremely big files. So bear that in mind. But they are available now. It's, I don't know, 30 years since it was done. A lot of it was published in journal papers anyway. But a lot of the underpinning work and the background isn't. It's in the reports. Certainly encourage people to think about that. Then as time went on from that, we got more and more involved with the European community, with the EPMA for myself, and that led us on to all kinds of projects, joint projects, European projects. We did one on very fine grained hard metals, which was done with a German company, which had Leo Prakash in there. You all remember Leo. We did a project on titanium-based cermets, which is of interest because one of the things that we did was make a multi-component carbide to rather than have this sort of titanium tungsten carbonitride materials, we had a 5-element material that was made by London and Scandinavian, and we managed to make that into a hard metal, and it had very interesting properties. So we didn't call it a multi-component project then, but that is what people are interested in very much so now. That again is all written up in papers that in reports. I think I did also a paper, but there are extensive reports for those projects. Now, because they were EC projects, I'm not quite sure what the protocol is for getting access to something that was in the late 1990s, say. Which I think now brings us up to the current system that we have. And we no longer have the British Hard Metal Research Association funding our work formally, but we do try and report some of the metrological work that is of interest to the industry at meetings where we just invite people that we've met or at conferences or people that we've seen written papers, etc. That's harder and harder to keep going because for our sins, the materials groups at MPL are not as big as they were when I first joined. When I first joined, about 1/3 of MPL was all related. The work there was all related to, in some way, to materials, and it's far less than that now, because things change. MPL has other groups that have grown from very small starting, but are thought to be important. Like biotechnology, for example. There was almost no biotechnology when I started, but now it's quite a big part of MPL. And as MPL has not really grown that much, it's been about the same all that time, then it's harder by the days to keep the materials activities going. But nevertheless, there are 4 or 5 of us who have an interest in this material and can contribute to the community, particularly through joint projects with the EPMA. I think, Suzanne, that's at least given you some idea of the beginnings, which is the
Thank you. Well, Brian, the other ones have added some parts that they thought were disruptive in the development, and listen to you, then I guess that the scanning electron microscope, especially for the fine-grained material, was a game changer, I guess, and because I think this is important to line out also, because sometimes you forget that you need also this equipment to understand.
Yes. I'd just like to make a comment there. Whenever people who don't know anything about the industry ask me about what I do, I have a little story that I say, and it's about when you look at a cutting tool and you look at maybe a few millimeters cubed part, you ask yourself how many grains of tungsten carbide there are in that very small range, and it's 10 billion. And if you ask someone how many stars are there in our galaxy, it's 10 billion.
Yeah.
And how many galaxies are there in the universe? It's 10 billion. So it's a very nice story to try and elucidate the material.
This gives you a perspective, absolutely.
Yes.
So, thank you. Björn, if you please turn on your camera. Can you do it?
Yes. I will. Okay.
Yes, I would like to say thank you to you all. This is really fascinating, and I'm learning today still. I just love it. I have a question that has been asked. It comes from Louise Janis, and something that has been really on the discussing, and you can see at least when it comes to publications, it has been a regained interest in looking at substituting tungsten carbide, and especially the cobalt part, with something else. And so we have a question from Louise: if you think that we will be able to substitute the cobalt in the future. And now having you here, Björn, who are one of the pioneers in the alternative binder phase diagrams, I would like to hear your first, and then the other.
That has been a long ongoing question. We started already in the 70s, I guess, because of the price fluctuations at that time of cobalt, but also later on the environmental hazards, the handling cobalt. And we have tried many times to exchange cobalt for nickel and iron. And as you may know, it's a tricky thing, really, but you can find combinations of nickel and iron which gives you allowance to solidify the part from the sintering temperature down to room temperatures without any extra phases precipitated, eta phases or graphite or whatever. But you see, cobalt and tungsten carbide, they match each other extremely well. You have the wetting, that's one thing. And also the properties, the ductility of the binder phase. There are so many things linked to that. So as Palmqvist, who was the head of research at Fagersta in many years, he made a presentation with a nice drawing showing that you will never find a marriage that lucky as that between cobalt and tungsten carbide. And I think we are still there. Maybe you can, maybe as you are on, Susanne, are changing the morphology of the tungsten carbide, maybe you can alter combinations with binder phases. But I have no answer. You can find a suitable phase diagram. That's one thing. But the other thing, there are so many other properties involved in that. So it's difficult to find a combination which is good enough. I think you maybe will be forced to replace cobalt because of environmental reasons later on, but you cannot do that for any application. Come to the rock drilling people and say you will not be allowed to use cobalt. What will happen then? Yeah, it will be many steps backward, I would say.
Thank you, Björn. And Colette, I think, has a comment. Are you muted, Colette? So we have to unmute you. Can you turn on the sound, Colette? You have to unmute.
Is it okay?
Yes. Now it's okay.
So-
So start from the beginning.
Obviously, we work in collaboration with Björn on this binder phase composition. The idea of the iron nickel mixture came from the fact that we found that we can have exactly the same electron structure between a special composition iron nickel and cobalt. And this was used when I had a study on catalyst. It was good, it gives good results for catalyst, but obviously when you go to the hard materials, the interface with tungsten carbide is different, and both the mechanical properties of the binder and the interface features are different. And as we said, as it was said, cobalt is still the best.
Yeah. Brian or Henk, would you like to know?
Well, I fully agree that there was a lot of laboratory work done in the past, also by Widia, but also later on in the Fachverband with different companies together with Walter Lengauer to find alternative binders. And so far, let's say on a laboratory scale, it was very interesting, but the sintering window was always the problem for huge mass production of these products. There were some very interesting applications, but I think personally that the way to go for other materials would have been better to focus more like the Japanese did on the ceramides, also including of cobalt, of course, but to have really alternative replacements of tungsten carbide, for instance. There was already, I have another computer here by Hinuber, Dr. Hinuber, in March 1965, a hard metal combined of 45% of titanium carbide thick, and very surprisingly 45% of vanadium carbide. And that was combined with an iron cobalt nickel, where the iron and the nickel were the main components. Thus you got away, like Björn said, away from this good marriage tungsten carbide cobalt, and you use here titanium carbide and vanadium carbide. This was very shortly introduced by Widia, but then on the first International Carbide Conference in Chicago in 1971, there were the coatings introduced.
Okay.
And coating, of course, gives a much easier jump to have better performance than this then starting complicated way with high titanium carbide and iron nickel cemented carbides.
Yeah. Thank you very much. I was thinking, Brian, would you like to make a short comment? I found one more question here in the chat that I would like to ask before we finish. Would you like to make a short comment, Brian, on alternative?
Yes, perhaps just one, and it goes back to the use of infiltration to make materials. We made rather a lot of different compositions, and I don't think that we really analysed everything that we could have done at the time. But one of the things that we did was to measure the Palmquist crack length against the hardness, and there's a usual plot that people plot for these materials, and as Jose Garcia has recently shown, you can get some very useful plots by looking at the whole population of publicized material. But having said that, some of the materials that we infiltrated did have better properties than the standard tungsten carbide cobalt. And one of them in particular took my eye recently when I was looking back at a paper. And it was one where molybdenum was involved. And you could see on etching the structure that there was a boundary around the outside of the tungsten carbide grains. There was clearly tungsten moly carbide. Now, was that structure something to do with making it by the infiltration method? Or was it something that you would get if you tried to make a material with molybdenum in there into the binder phase initially? And I'm not sure, I think if I had the time and resources, that's certainly one thing I would go back and have a look at. The other thing, while I'm talking about this and making materials, is another point which I think is worth visiting. One of the other objectives we had was trying to look at thermal fatigue properties. So this is going off the ball a bit. And one of the things that we did was rotate hard metal specimens underneath an electron beam. Our workshop had an electron beam equipment, and I'm going back now 20, 30 years. And as you rotated it, this is in a vacuum, so you've got no oxidation issues. The surface is exposed to incredibly high temperatures for very short periods of time. And the structures of the material in that EBM affected zone were like nothing I've ever seen before or since in tungsten carbide cobalt. And now when you think about additive manufacturing technology, it's in a way, could you use that to modify the surface of a sintered material to produce an unusual surface that would have interesting properties? And that's certainly, being an old person, there's no way I'm going to have the time or the resource to do that. But I think that would be, something that wouldn't be difficult to do, and would certainly provide some insight into microstructures affected by rapid heating.
Thank you very much. We are running a little bit late. I hope that's okay for everybody. Kenan, do we have room for one more question? Or?
Yes, of course. I think we can go on for 5 minutes more. Yeah.
I have several chat in the chat here. There's a lot of discussion also about recycling and concerning the future, where sustainability is an increasing demand everywhere in the society, and also the obligation to recycle more. I was just curious because I know that many of you, at least in the public domain, what I know, have looked at impurities within cemented carbides. Both Björn and Brian and Colette, I know Henk was in a competitor company, so I don't know what Henk had done. but I think that if I guess that all of us kind of guess that it will be an increased demand on using recycled material in the future, and we heard Colette mention the zinc reclaim process. How important, just out of your vast knowledge, do you think that that the research and the impact when it comes to impurities in the cemented carbides will be in the future? Maybe, I don't know who would like to start. Henk?
Well, what we did when I joined Widia in 1980, I was very surprised in the cemented carbide production that we already had a grade called TTR with 12% cobalt and using 75% zinc reclaim material.
Mhm.
What happened, call it impurity, was that of course a lot of these very tough grades in those days were coated with thicker titanium nitride layers. So having all this titanium nitride layers, we all of a sudden had free carbide zones in the cemented carbide top layer because of the nitrogen
Yes.
diffusion, what happened then. But it was amazing to see, because of course, using 12% cobalt, how this grade, and also after that coated was this grade by us, was performing. So 75%. In the P15 and M15 grades, we decided then very quickly to introduce 55% zinc reclaim material. So it was growing very, very hard. The key point was that on the average, we had 8% cobalt in this zinc reclaim material. But the most important thing was an absolutely analysis, a very, very close analysis, and then have a calculation program what gives you what we have to mix within it, tungsten carbide, clean, cobalt clean, whatever. But it was amazing how this was performing at the market. And in one step, we had even a solid carbide drill made out of 100% of this 8% reclaim material, but very, very dense controlled. And it is very nice to see that in a paper given by Uwe Schleinkofer of Plansee at the Hagen Symposium last November, he had a very nice overview of the usage of reclaim material, also using zinc. And it seems to be that this is one of the right ways in the future regarding sustainability. And I was really very happy to see this article of Uwe Schleinkofer. So yes, you can use the zinc reclaim process, but of course you have very, very carefully control your product, what comes out of it, and then make the right calculations how to make a new product.
Mm.
Any comments from Jade? Thank you. Henk? In this case, I would also like to remind us all, because it's also one other thing that I think you forgot to mention it, Brian, but I think it's a great help to the Hard Metal Society as such. It's the best practice handbooks that was created by the National Physical Laboratory, that I think that all of us within the industry has used. And every time someone asks, you pick out the handbook, the best practice guide, and give it. So I think this should be mentioned, not forgotten.
Mm.
With this, I think we are. Yes, Björn, do you want to?
Oh no.
And I really want to add. I hope that in the audience and the people that joined, that we have a revival out of the cemented carbide industry in Europe to push and to support these so-called projects, what we can do within the EPMA together, without, of course, telling the secrets of our own company. But these projects are really very helpful and useful for our industry. So I hope that this finds again a way that these projects are restarted or have a revitalization, whatever, because they were very, very good.
Thank you.
Thank you very much, Henk. With this, I would like to hand over to you, Brian. Can you hear us, Brian?
Sorry, Suzanne, I didn't hear
I would
that.
like to, because we are we're coming to the closing of the webinar, so I would like to hand over to you for the closing.
Still can't hear you. I've something gone wrong with my loudspeaker, I think.
I can hear you. Can you hear the other?
Yes, I think I can try. Can you repeat?
Yes, I would like to
Sorry.
hand over to you for the closing of the webinar.
Oh. Yes. I was expecting more questions from the audience, Suzanne.
Yes, but I think we are maybe
a little bit
15 minutes
over
now.
time. Yes. So
If
thank you
have
for everyone.
Yeah, sorry. Just if you have questions, you can still post them in the chat, and we will try to answer the best we can. Please, Brian, go on.
Yes. Okay. Well, thank you everybody for listening in to what some oldies have to say. I hope they found it interesting, and I certainly enjoyed speaking to Bjorn, Colette, and Henk. It's a long time since
Very
I've
long.
spoken to them in person, and it's great fun.
Very
Nice to
30
see.
years maybe.
So if everybody enjoyed it as much as I did, then it'll be a good meeting. And you can record. You can look at the recording anyway. So thank you.
No, thank you all.
Yeah. So thank you, everybody listening. And if you wish, you can turn on your cameras so the presenters can see you if you want to. And with this, we would like to close the webinar. Thank you.
Okay. Bye-bye.
Bye-bye.
Bye.
Bye-bye.
Bye.
Bye.
Thank you. Bye-bye.
Thank you.
Thank you very much.
Thank you, well, you were fantastic. Happy to see you.
Okay, thank you very much. People are leaving, but I really would like to thank our speakers, Colette, Hank, and Björn, especially you and Brian, Susan. This is really